7, we're asked to use the limit comparison test to determine whether this converges or diverges. So we know that to do that, in the limit comparison test, we first identify what we're going to compare it to. And we're going to compare it to the dominant term in the top and the bottom. So in the top, we can easily see that k squared is dominating what's going on there. In the bottom, these are under the square root, but k to the fifth is going to dominate. So I do need to keep it underneath the square root. And simplifying this so I can identify whether this converges or not, I can see that the bottom is k to the 5 halves. So I'm going to write the top as k to the 4 halves. And then I subtract those exponents and I end up with k to the 1 over k to the 1 half in the bottom 1 half. And this we recognize is a divergent p-series because the p is less than 1. And then for the limit comparison test, I compute the limit as k goes to infinity of my original general term divided by, it's best to use this non-reduced form, so divided by my general term of the series that I know something about. I know that this general term, when I take the series, it will diverge. All right, and then I flip the bottom and collect factors that sort of have the same terms in them. So the k squared plus 2k plus 2 goes here. That's k squared. And that's divided by the k squared that'll flip up here in the top. And then I've got my square root of k to the 5th that I'll collect together with this one. All right, and this one I can do algebraically by just separating it, but I might as well use rates of growth. Those two things are the dominant terms. Since they both have a coefficient of 1, it'll go to 1. And again, that's because these two things grow at the same rate. This is sort of the same. I can write this as a single square root, and then I can identify the dominant terms underneath that square root, and the fact that k to the 5th and k to the 5th plus this other stuff grow at the same rate. I'm going to get the coefficients on the k to the 5th under the square roots, so I'll get square root of 1, which is still 1. So I get 1. And that's important to note that this is finite and it's positive, and that's what we need for the limit comparison test, is this limit to exist. And when that limit does exist, my series will do the same thing as the series I compared it to, which is diverge. So the limit comparison test here says that I have a divergent series. Number 8, we're told to use the integral comparison test, the integral test to determine whether this converges or diverges, and we're told the function, which is no mystery. We use the same function that kind of matches up. And I'm giving you a hint on how to evaluate the integral you're going to have to do. So, but we don't have to do this extra stuff here of showing it's positive, continuous, and decreasing. Well, the integral I need to evaluate is from 1 to infinity of 1 over 1 plus x squared tangent inverse of x. And so to set it up properly, that's the limit as r goes to infinity of 1 to r, 1 over 1 plus x squared tangent inverse of x. And so then we've got this integral to evaluate, and that's what this is saying. Substitute for, not for f, but I guess I should have said tangent inverse. I'll fix it before I show it to you. Consider substituting for tangent inverse. And that's one of our rules when we were doing integration techniques, is if there's a tangent inverse in your integrand, you either need to substitute in for it or you're going to use integration of parts. And so I'm just kind of reminding you that here. When I substitute in for it, the du here becomes 1 over 1 plus x squared dx. And so it's set up nice to where that's exactly what I'm going to have left over when I substitute in for it. So this becomes the limit as r goes to infinity. I'm just going to have a 1 over u because the rest of this is going to go away as du. And I do need to change my limits here. So tangent inverse of 1, which is pi over 4, and tangent inverse of r goes in the top. And so now I can evaluate this. This will be the limit as r goes to infinity. I'll have, this is going to become natural log of u evaluated at pi over 4 here in the bottom, and tangent inverse of r here in the top. And so I get the limit as r goes to infinity of natural log tangent inverse of r minus natural log of pi over 4. And so I figure out what happens. Well, natural log of pi over 4 is some number. Natural log of tangent inverse of r. So that one we have to think about what's going on here. So as r goes to infinity, this will go to pi over 2. And so I get natural log of pi over 2, which is a finite number. So this does give me natural log of pi over 2 minus natural log of pi over 4, which is a finite number. And so that says that this integral converges. And if the integral converges, then so too does my series. So that implies I get convergence of my original series.